yaptığın anda kaydı da başlatabiliriz.
Tamam. Ekranımı görebiliyor musunuz?
Ben görebiliyorum.
Tamam. Yani oynatıyorum, şöyle gözüküyor herhalde.
Evet.
Sunum
Tamam.
slaytları şeklinde açıp başlatabiliriz.
Tamam.
Hı hı.
Okay. For my presentation, I will talk about audio and video codecs and ways to improve them using filters. First, we all know the video files, right? Like MP3 files, MP4 files. These are actually called containers. These containers can hold single or multiple media streams. Some containers exclusively hold one type of streams, like MP3 files that can only hold MP3 music or FLAC files, while the others, like video, mostly video files, can hold multiple media streams. They can hold audio streams, multiple audio streams, and video streams, and even subtitles. Now, for video containers, we have first we have MKV, which is Matroska. It's an open format that can contain virtually any kind of stream. You can give it anything to it, and it will hold it just fine. There is MP4, which is widely available. This can hold H264, AV1, VP9 video codecs. I will talk about these codecs later. And AAC, FLAC, Opus, and MP3 audio codecs. There is also WebM. This is similar to MP4, and it can hold AV1, VP8, and VP9 video codecs, along with Opus and Vorbis audio codecs. For audio containers, we have FLAC, which is a container for FLAC codec, and for A, which is the audio part of the MP4 that can hold AAC or LAC codec. And there's DSF, which is actually different from these containers, and it holds DST signals. I will talk about DST later. Well, codecs are actually compression methods of these streams. They can be lossy or lossless. Lossy codecs will lower the quality of the source material, but they will offer significantly smaller size, like from gigabytes to megabytes. Lossless codecs will retain the quality of the source streams, but they will have larger sizes. But you can encode and decode them without any loss of information. For video codecs, let's talk about what videos are for a second. We know that videos are actually sequence of images, and they have this thing called frames per second, which means like if a video is 60 frames per second, it will have 60 different images for a single second of video. Now, if we think about this, this takes up a lot of space. To accommodate that, instead of redrawing the entire screen, we can actually divide the screen to parts and only update the chunks that are in motion. This is called a block-oriented coding, which most video codecs use. First one is H264, in other name AVC. This is such codec that divides the screen into chunks. This is the most common video codec. Like the most devices we have in our hands will decode this just fine. And there is HVC, which is H265 in other name. This is an improvement over H264 that supports variable sized blocks. What this means is, on the left side, we see a picture of a dog and some grid on top of it. These grids are actually chunks of the video, and only the moving parts are updated. But in variable size blocks on the right side, we see that the still parts of the image is actually have larger chunks, but the moving parts have smaller chunks. This actually saves up around half the bit rate at the same while delivering the same quality. Like this will have around the half the size of H264 encoded video. This is not widely adopted due to high licensing fees. I think only Apple devices support it at the moment. I mean, the decoding and encoding. And we have some open video codecs. First one is the VP8. This is much like H.264, also block-based. This is not terribly great on high resolutions. It doesn't support many color gamuts or HDR or something. So it's mostly aimed to replace the GIF format, which is displaying frames of image one after another. There is VP9, which is a successor to this VP8, and it is a competitor to H.265. It's comparable to H.265, but because it doesn't have licensing fees, it's widely adopted. And we have AV1 at the end, which is a successor to VP9. And according to Facebook's benchmarks, it's 35% to 55% more efficient compared to VP9. Most video streaming services such as YouTube, Netflix, and even Facebook use this format to deliver videos, and more streaming services such as Twitch will support this in the future. For audio codecs, I will talk about in this slide the lossy stereo codecs. The first one is AAC. It's the successor to MP3. It's widely adopted, like it's really ubiquitous. Like any portable device will decode this format just fine. And there's Opus, which is a successor to OGG Vorbis, which was an alternative to MP3. Which was actually comparable to AAC. This Opus format performs well at even extremely low bit rates. Like at 16 kilobits per second, you can still recognize human speech. Because of this and its lower latency, it is preferred by voice call services such as WhatsApp and Signal. I think Telegram and Discord also use this format. And for lossless stereo codec, we have FLAC. It can compress the main stream from 50 to 70% depending on the compression, and it's able to decode quickly independent from the compression level. There is also ELAC, which is a lossless format by Apple that is comparable to FLAC in compression levels, but it requires around 4 times more CPU power to decode it. So it's not that better than FLAC. And there's also DST. DST is actually a lot different than our conventional formats. It uses delta sigma modulation to deliver the signal instead of pulse code modulation, which is PCM. Let me show you a quick comparison. On the left side, we see a PCM signal, which is sampled at 44.1 kilohertz at 16-bit depth, while in the right side we see DST, which is sampled at 2.8 megahertz, but only at 1-bit depth. This is just a different way to deliver the audio signal. To process this DST signal, you need a specialized hardware like higher-end audio cards or digital to analog converters. You can also convert this format to PCM, but there will be loss in some information, so it's not generally preferred. This is not a common format, and it's mostly adopted in Japan through the distribution of super audio CDs. I think in Germany and other parts of Europe, it gained traction somewhat, but it's mostly used in Japan. For surround audio, we have AC3. It's a lossy format by Dolby Digital that can hold up to 6 channels at 640 kilobits per second. And there's a competitor to this called DTS, which from Digital Theater Systems. While theoretically this can support 1500 kilobits per second, it was mostly encoded in 750 kilobits per second to make room for more audio tracks like different languages and such. So it's not so different than AC3 in terms of quality. For lossless, we have Dolby True HD, which is by Dolby Digital, that can hold up to 8 channels at 18 megabits per second. And DST can also hold 6 channels at around 20 megabits per second. It was distributed along with the stereo mix in Super Audio CDs. I showed this comparison. And I will talk about filters, mainly video filters, because we actually benefit from them compared to audio filters. Audio filters are mostly used in music production, so it's not really important to us at the moment. There are low pass and high pass filters to reduce microphone gains, but other than that, we don't really benefit from them much. So I will talk about video filters in this video. We have the interlacing. I will talk about this later. Denoising to noise, remove the noise from the video. There is also deblocking, which is used to decode the video codecs, and frame on interpolation, which is doubling the frame rate of the videos. First, to talk about the interlacing, I'll have to talk about what interlacing is. The screens we have today are actually progressive scan. We in a single frame we get the entire picture, but in interlaced signal, the screen is divided by half. We first have odd lines and then even lines, or it was the other way around. I'm not sure. I'm not so sure. But if the signal is at 60 hertz, at first we see the even lines and then the odd lines. They are alternating between each other. Normally the CRT TVs will display this signal just fine, but to see this signal in our screens, we need the interlacing. So yeah, which converts this signal to progressive. The interlacing has mainly two methods. Which first one is field combination, which is combining these fields to make up a one frame, and the other is field extension, which is either removing the gaps between the lines to create a squished image or doubling the lines. First, for field combination, if our source video is at 30 frames per second, we don't lose any information or gain any artifacts by combining these two fields together. But if the source video is at 60 frames per second, we will see this combing effect at the right side of the screen. The reason why this happens is the bottom lines will be one frame ahead of top lines, so this creates this effect. There's this is called just combining these two lines is called the weaving. There's also blending, which is taking the approximate of these two lines and then creating a single frame. But this creates another issue called the ghosting. I talked about line doubling and half sizing. To show this weaving, I actually captured some footage from my PlayStation 2 system. I used this script to capture, which you can reach from this link. I'll just show you briefly the code. Okay, in this code, I just declared some variables to declare the properties of my video capture device, and used a GStreamer to create two pipes, which is one pipe is forward to a Matroska file, MKV file, while the other is pipe to FFplay, so I can actually weave what I'm capturing. I'll show you the original weaving capture, but I don't know if you can notice much from my screen sharing. If you the combing effect is really apparent in this video, but I don't know if you can see it. You can always download it from this link to see it for yourself. To fix this, I used two filters which do line doubling. I used a FFmpeg for this process, which is a holy grail for video processing. First, I used the YADI filter, which stands for yet another the interlacing filter, and Bob weaving the interlacing filter. I'll just show you show these videos to you, but I don't know. I still don't know if you can notice any difference between them. But you can always download it for yourself. This is YEDIF. It is much smoother than the original viewing capture, and it doesn't have those combing effects. Same with BFDIF. They're actually not so different, but I generally prefer YEDIF better. But it's up to preference. Now I will also talk about frame interpolation. Frame interpolation actually doubles the frame rates like this. At the top row, we see a regular video file. Like there are frames going on. Let's say if this video is 30 frames per second, the first frame and second frame is merged together to create an intermediate frame, which is then put together between those frames. So this effectively creates a 60 frames per second video from 30 frames per second video. For this, I use the motion interpolate filter of FFmpeg. At first pass, as I use the most basic options, which is blending. It took me 6 minutes to process, which is short compared to the other method. I also used the Big Buck Bunny short film by the Blender Foundation. But because this was a weak, I used weak options, it's not really apparent that this is interpolated. But in the second pass, I use a lot of options, like I utilize all the options given to me, and this took me 4 hours to process this 9-minute video. But in the end, you can see that it's much more fluid, like in this video. I don't know. I still don't know if you can notice any difference. I'll just uploaded the videos so you can check it for yourself. While this creates while this okay, let me compose myself for a bit. While this doubles the frame rate of the video, but it has its own flaws. Like if the one frame, like the spacing between these 2 frames is too much, the estimation of these 2 frames will be not great. So this will create artifacts. You will be able to see it on the corners of this video file, the artifacting. I think there is also more filters than motion interpolation. There is also smooth video project, and NVIDIA was starting to experiment with this to be used in video games in their DLSS 3 technology. And that's it about the things I will talk about. I will be glad to have your questions.
Thank you very much, Furkan, for your impressive presentation. Actually,
thank you.
It was very impressive in terms of me, and yes, your presentation had got a lot of explanation about the codec, video codecs, audio codecs, and filtering part. Is there any question from other students to Furkan?
I can also explain some parts in Turkish if it's not really clear. Yani Türkçe olarak da açıklayabilirim arkadaşlar, aklınızda bir soru kaldıysa.
Çok teşekkür ediyoruz Furkan. Gerçekten ben çok beğendim sunumunu.
Ben teşekkür ederim.
Gerek açıklamalar anlamında, gerekse kodla birlikte birleştirdiğin demolar kapsamında oldukça etkileyici bir sunum olduğunu söyleyebilirim.
Çok teşekkür ederim.
Soru yoksa eğer bir sonraki arkadaşa geçelim.
Sanırım yok.
Sanıyorum yok, evet.
Kaydı durduruyorum.
Tamamdır.